Alright, welcome back. Today I'm going to be completing part B of homework 3 for separations. What we're going to be doing today is we're going to derive an expression for the boil-up ratio in terms of the liquid fraction of the feed, that Q that we had talked about in our previous video, as well as the reflux ratio R. And to help us along here, I've drawn our schematic for our overall distillation column with a total condenser, as we're going to need a couple of those expressions that we derived previously in part A to do our analysis here. So getting started here, looking at our overall rectifying section, as we've discussed before, everything coming into our rectifying section, which is our V, equals our liquid coming out plus our distillate we're pulling out. And that's the overall material balance for just the rectifying section. We're going to need that a little bit later. We also need to consider our feed section. So what do we have coming in and coming out of here? Well, if we look at it, we've got the vapor portion of the feed, so we can say 1 minus Q, Q is the liquid portion of the feed, times F, plus we've also got V bar coming into our feed here, equals our V. And then subbing in this expression that we were talking about is the overall material balance for our rectifying section. We get that 1 minus Q times our feed F plus V bar equals L plus D. Furthermore, subbing in our reflux ratio R, which we've previously discussed is L divided by D, we can get that 1 minus Q times F plus V bar is going to equal, what is this? So we got 1 over D. Equal R plus 1 times D. That's correct. Going on from here, we also know that our boil-up ratio, our VB, equals our V bar divided by our B, our bottom flow coming out of our reboiler. And subbing this into our expression here, once we're going to go ahead and arrange for V bar first, just to make this a little bit easier. V bar is going to equal R plus 1 times D minus 1 minus Q times F. Then subbing in our boil-up ratio here, we can get that VB equals R plus 1 times D minus 1 minus Q times F, all divided by our bottom's flow B. And this right here is our first expression we were looking for, the expression for our boil-up ratio VB in terms of our reflux ratio R and our liquid fraction of the feed Q, meaning that we have all of the overall material balance flows. We got our distillate flow, our bottoms flow, and our feed, and then just our reflux ratio and our liquid fraction. So now that we have this expression, I'm going to go ahead and erase all of this work, and we can move on to find our expression for the equilibrium liquid fraction given the vapor fraction of the more volatile component, as well as assuming that we're dealing with a binary mixture with a fixed relative volatility. So let me go ahead and erase all this and move on to derive that expression. So to get started deriving this expression, we need to first look at our value for our constant relative or fixed relative volatility, alpha, as we discussed previously, which equals our x1 of our more volatile component over our y1, which also equals x2 over y2, as this value is fixed as we were saying before, which also means that it equals 1 minus x1 over 1 minus y1. As for a binary mixture, these two values are equal. So rearranging this to get our two common values here, our x1 and our y1, we can say that alpha is going to equal y1 times 1 minus x1 over x1 times 1 minus y1. Multiplying this out, we can get that alpha x1 minus alpha x1 y1 equals y1 minus y1 x1. And then rearranging this to solve for x1, we can go ahead and pull this out. We can get that x1 times alpha minus alpha y1 equals got a little ahead of myself here. We're also going to want to move this y1 x1 term over to this side so that we can, like I said, isolate our x1. So we can say that alpha x1 minus alpha x1 y1 plus x1 y1 equals y1. And as I was saying before, once we factor out this x, we get that x1 times alpha minus alpha y1 plus y1 equals y1. And then, as you can see, we can solve for our x1, which is what we're looking for here, equilibrium liquid composition. It's going to equal y1 over alpha minus alpha y1 plus y1. And that is the expression we're looking for here. So now we can go ahead and move on to the next part of part B. All right, welcome back to the Python portion of this video. And what we're going to be doing for this second part of Homework 3 Part B is we're going to write code to automate the generation of McCabe-Thiele diagrams for a distillation column with constant relative volatility and a total condenser. And then we're going to use our code to demonstrate what happens to our McCabe-Thiele diagrams and the overall equilibrium at relative volatilities of 2 and 5 and at decreasing reflux ratios going from 1000 down to 2 down to 1.5 all the way down to 1. So getting started here, we're going to need to put in all of our basic metrics. So start off with the feed F. We're just going to say 1 mole per second. And then our ZF, we're going to call 0.45, which is our feed composition. Then, of course, we need to put in our Q. And to start off here, we're just going to say that our Q is going to be 0.9. So we have 90% liquid in our feed. Going on from there, we need to go ahead and define our recovery in our distillate. So we're going to say our RD is going to equal 0.95 because we want 95% recovery in our distillate. And then we're going to go ahead and define our XD, which is our liquid composition in our distillate. And typically what you're going to want is like pretty much with a total condenser all liquid, but we're going to call this 0.998 for now. And then going on from here, we also need to define our reflux ratio, R, which, as we said, we're going to go through decreasing reflux ratios, but I'm going to start at 2 because I have a feeling that 1000 is going to be one of our edge cases where our diagram is going to look real ugly. So we're going to start at 2 so that our first diagram we end up making looks pretty nice. So it's our reflux ratio. And then going on from our reflux ratio, we need to define our constant relative volatility alpha, which we will keep it 2 at first. As that's one of our cases asked for in the question up here. And then besides our relative volatility, we're also going to need our distillate flow, D, which is, hold on, what's happening? Distillate flow D, which is going to equal our ZF, our feed composition, times F, times RD, all divided by our XD value, because that's our recovery times our feed composition times our actual feed rate over our liquid composition in the distillate, which just comes from a material balance to find that distillate from our overall material balance of our feed and then our distillate and our bottoms flow. And as I said there, we're also going to our bottoms flow, B, we're just going to equal our F minus our D, again, from that overall material balance. And since we have our B, we're also going to need our XB, which is going to be our liquid composition of our bottoms, which also should be almost completely liquid, but this time we're going to calculate it using ZF times F minus XD times D, again, general material balance there, all divided by our bottom slope B. So that's our liquid composition in our bottoms. And we're also going to need our boil up ratio, our VB, which we defined on our board up here just before. And we will recall that that is going to be our F times our R plus 1 minus our B. I've got this all confused. It's our D times our D minus our F, because I was getting the reflux ratio and the boil up confuse our f times r1 minus our q value, all divided by b. And going on from there, we need to put in our stuff for our Q line. Once we start graphing that, we're going to need our metrics for a Q line. Also figured out in part A, we went through the whole derivation of how we got that that equation, but I'm going to go ahead and rearrange it a little bit in the code and put it in here as xq. Sorry, our xq is going to be our x values for our Q line, and we are going to define those as xb over our boil-up ratio, our VB, doing this algebra in my head, minus our xd, all divided by r plus 1. Looks correct. All of this is going to be divided by r divided by r plus 1. Parentheses in there. Minus VB plus 1 over VB. And that is the x values for our Q line. So now we can do our YQ, our y values for our Q line. Those are going to be r divided by r plus 1 times our x values for our Q line plus, add to this, our xd all divided by r plus 1. Those are our y values for our Q line. So finally, we're good to move on and do some actual coding instead of just putting in all of these equations that we have figured out over the part of this video and then all of part A. So hit a Shift Enter. I think I actually need to run all so that we get our CHE tools in here as well. Give that a second to load up. But while that's coding, we're going to define our x equilibrium func. I'm going to call it for now because we're going to have a lot of things called x equilibrium by the end of this. But just as we're defining our function, which is just going to be a function of y, as we talked about up on the board there. And now that we have that, we can just go ahead and return. Let me look up at the board here. So x is going to equal our y divided by, what I got up here, alpha minus alpha times y plus y. And that's just that function we figured out up here of our equilibrium liquid fraction in terms of our relative volatility and our vapor. So now that we have that, we can also go ahead and define a couple more little equilibrium functions here. So once we get to graphing our McCabe-Thiele, we know that we're going to need our YEQ for that curve right above our 45-degree angle. So in order to make it so that we can graph that later, I'm going to say our YEQ is just going to be mp.linespace going from 0 to 1 with 51 points in between. And then using those y values, we can define our x values for our equilibrium curve using the function up above. So we're just going to do x equilfunc y based off our YEQ values we are getting from that numpy.linspace function here. And that's going to make it so that later on we're going to be able to graph that equilibrium curve right above 45-degree angle. So that should be all good. And moving on, we need to create a for loop that'll go through and create our steps for our McCabe-Thiele diagram that is specified in our variables up here. So to do that, we theoretically are going to want it to find the amount of steps, the like max amount of steps that you want to go through before you get there. But like you typically wouldn't specify this, but just CSR, we're just going to say n max equals 50. So we are not going to want to go above 50 steps, as that would be an absurd amount of stages. And then we can initialize our XY list, which is going to be the list of those values we're going to use to plot our steps. Say our XY list is going to equal XD, XD, just so that we're starting way up at the top, and then we're going to move our steps going down to the bottom of our McCabe-Thiele. Now that we have that in there, we can define our Y equilibrium. Y equal, we're just going to call that XD. Now we got all those preliminaries in there. We can create our for loop that, like I said, we're going to use this for loop to go through and create those steps down our McCabe-Thiele diagram. So we're going to say for k in range n max, just that n max we specified up there. Don't think I want to have that period there though. So we're going to say for k in range n max. First thing we're going to want to do is define our x equal, which is going to use our x equal funct based off of our y equal values. Yep, looks correct. And then we're going to want to append our xy list. Because if you remember, we just started it out way up at the top, so we're going to append it with each of our new values coming down this list. Dot append, and we're going to append it with our x equal values calculated right above, as well as our new y equal values. Perfect. And now that we are appending that list with each of our new x equal and y equal values, we're going to want to break the loop once we hit, because we're going to have these two operating lines, and we don't want to get into a crunch where we're breaking down only in the rectifying section. We need to make sure that our function is going to hop from the rectifying section down to the stripping section when it makes sense to do that. So what we're going to do is we're going to say if x equal is less than xb, we're going to break our function. That way we're breaking out of this loop once we've got like our certain amount of steps that we actually need. And then we need to define our y rectifying, our y values for our, as we're hitting our rectifying line. We're going to create this for our rectifying and our stripping. So like I was saying earlier, we can make sure that we make that jump. This above function was not, I think I was explaining it in the wrong order, but this is just to break out, stop making more steps once we've hit our bottoms composition we're looking for. This next function, we're going to create our function for our rectifying line and our stripping line, and we're going to compare the two to see when we need to make our jump from the rectifying section down to the stripping section. So we're going to say that our y rec is going to be equal to our r times our x equilibrium divided by r plus 1. Uppercase R, and then we're going to add xd divided by r plus 1. And as we've been saying previously, these two equations are coming from our previous derivations for our column, for our rectifying section, our stripping section, just rearranged for it to work in the code here. So this would be that those functions we were talking in part A, we were talking about yn plus 1, the operating line equation, yn plus 1 for the rectifying and stripping. This is what we're doing here, is we're creating those two operating lines so that we can later go ahead and plot them onto our Mercatili. And in this case, we're currently putting them in here so that we can compare them and we can decide, okay, it's time to jump from that rectifying to our stripping section. I know I've repeated that a couple times, but it seems a little hand wavy, but like all of this information is coming from our part A. So anyway, continuing, we need to go ahead and put in our y strip values. So our y strip is going to equal our x equilibrium times VB, 1 plus VB, I should say, all divided by VB minus our XD divided by VB. And that's that stripping operating line function we figured out in part A. And then we can update our Y equilibrium value so that it picks the minimum between our Y rectifying and our Y stripping. So like as I was saying before, when it does that, once one of them exceeds the other, is going to jump from the stripping down, or from the rectifying down to the stripping section. So we're not always caught in one of the two sections. So say the minimum between our Y rec and our Y strip. Perfect. And we can do our final XY list append with all of this new information as we go through the loop, and we're going to again append it using our x equilibrium and our y equilibrium values. And that is going to, that loop, the entire purpose of that is to create these steps that we're going to need to use for our plot going down our McCabe-Thiele diagram. So now that we're appending those values, we can stick all those values into an array. So as usual, we're just going to say xy list equals np.array xy list. Cool. So we've got our entire for loop. We're going through everything, creating these steps, creating our rectifying and stripping line, making sure we're making that jump, all the really the engine, I guess, of creating these personal McCabe-Thiele diagrams based off of the information we're providing up here. So now we can go ahead and create our McCabe-Thiele plot, or create the functions that will create our McCabe-Thiele plot. Alrighty, what's happening here? I see what I've done wrong here. I put parentheses up here, which we are looking for brackets. All right, Shift Enter. Ooh, we're all good. All right, so now we can move on to creating our McCabe-Thiele diagram. So, as per usual, we're going to do our figure equals make subplots. And again, as per usual, the first thing we're going to add to our figure here is going to be that 45-degree angle because it's the easiest. So I'm going to do fig.add scatter. Have our x's are going to equal values from 0 to 1. Our y, oops, forgot a bracket there. Our y's are going to equal values from 0 to 1. And our mode is going to equal lines. And our name is going to equal our 45-degree line. And then we can go ahead and add our next, which of course is our second easiest because we've already done the calculations for it up here, which is going to be our Q line. So fig dot add scatter, not our Q line, our equilibrium curve, I should say. And we're going to have our x equals xeq. Our y is going to equal yeq. Our mode going to equal lines. And our name is going to be our equilibrium line. I can't spell for some reason. Equilibrium line. All right. And then up next, it's a little bit tougher because we're going to add our rectifying and stripping lines. So we're going to, again, kind of rearrange these equations up here in a way where we can plot them easily integrated into this fig.add scatter function. So we're going to say fig.add scatter, and our x's are going to be going from, I think it's 0 to our final xd. And then our y's are going to equal our, careful parentheses bracket work here, our xd over r plus 1 going all the way to up to xd. Oops. Way up to xd. Cool. All right. Then our mode, as always, going to be lines. And this is going to be our rectifying line. Rectifying operating line. Perfect. And then we need to add our stripping operating line. There's no way. No, it did. The AI does not have it correct. Fig.add scatter. And this time around, we need to put in our x's. X is going to equal, we're going to go from our xb, which is going to be our bottoms, of course, starting at the stripping, going from our xb. And then we're going to go all the way up to this function here. We're going to do bb plus our xb. So I'm being very careful about my algebra here. Over 1 plus b looks, I believe that's right. I'm sure we'll find out here soon though. And then our y's, of course, we are just going from our xb, our bottoms composition, all the way to 1. And then our mode, as usual, is going to be lines, and our name is going to equal our stripping operating line. And then next up, we of course need to add in our steps. We're going to do fig.add scatter x. Oh, I think the AI got it right that time. Yep, x saw the first value in our xy list array, second value. Yep, so x equals xy list going from our 0 value. I think that's the right syntax. Our y equals our xy list at our second value. Our mode is going to equal lines. And our name, we're just going to call this steps, as that's our steps going down our operating lines between our operating lines and our equilibrium line. And then finally, of course, we need our Q line. do fig.add scatter. For our Q line, our X is going to equal our ZF along our 45-degree angle XQ, calculated that way up at the top. Our Y is going to equal ZF YQ, unsurprisingly. Our mode is going to equal lines, and the name is going to be our Q line. Perfect. And I believe that is all we need. So we can go ahead and do fig.update layout, because I already know this is going to be a lot of information to cram into whatever it defaults at. And we're going to do our width equals 600, height equals 600, then title is going to equal our McCabe teal diagram. And I believe that's everything. Fingers crossed, shift enter. Whoa! What's happening here? All right, one moment. All right. Hold on. Go ahead and run all. Here we go. So, as I was thinking, my initial values were kind of crappy, so I went ahead and just like shifted those around a little bit, and now we've got our very pretty McCabe teal diagram. As you can see, it perfectly shifts going from the stripping section down to the rectifying section in a fair amount of steps. So now that we've got our code to generate these McCabe teal diagrams, let's go ahead and play around with it a little bit, see what happens when we go through these different parameters. So first off, let's try a relative volatility of 2. See what this does. So as you can see here, keeping the reflux ratio the same and changing our relative volatility up makes it, or shifting it down to 2, makes it so that the relative volatility of the two substances are very close, meaning that the separation is extremely difficult. And in this case, it is impossible to get even from the rectifying to the stripping section. That's why you see we are stuck here in our rectifying section. We can never make the jump down to the stripping section. But on the contrary, if we shift our relative volatility all the way up to 5, here you can see the separation becomes extremely easy. It becomes trivial almost. We have very few steps. We're jumping, making huge jumps, huge steps. We're able to separate very easily with very few stages in our column. So now that we've seen the implications of our relative volatility, I'm going to put it back at 3 so that it's back in the middle. And now we're going to play with our reflux ratio. And first thing we're going to do is we're going to set it to 1,000. Pretty absurd number. Let's see what that does. And clearly here, when your reflux ratio is 1,000, you're dumping so much of that liquid back into your column that the operating and stripping lines essentially just go down directly to that 45-degree angle, and your separation becomes very easy with very few stages. But on the contrary, in an actual column, if you had that high of a reflux, you're not pulling out very much distillate or like so much of your flow is just coming back into the tower, which leads to some higher energy costs, stuff like that. So going from 1,000, well, we just saw what 2 looked like, so let's bump it down to 1.5, see what that looks like. So as you can see, with a lower reflux ratio, you're tossing less of that liquid back in your column, and you're pulling out more distillate, but your separation becomes much more difficult without that reflux in the column. We're having a lot more steps, and that pinch point is getting real close to where it switches over there, and our operating lines are very close to going over our equilibrium line, making separation nearly impossible. So let's see what happens when we go all the way down to 1. Bang, yeah. Same as when our relative volatility was really are really low. If our reflux ratio is really low, it means we're dumping, we have very little reflux. We've got very little cycling going on in the tower. We're getting that composition up, which makes it hard for us to get past just the first stages of the rectifying section. We don't end up being able to make it all the way back down to our bottoms composition. So I think that about does it. We've got our McCade-Teal diagram. We went through and gone through all of these different conditions. So I think that finishes out our separations homework 3 part B. I will see you in part C, where I think we're doing some Fensky Underwood derivation and doing a little bit of coding related to that. So I'll see you in the next one.